So I'm very excited to be here. Thank you everyone for coming. Great. So as you all know, Kaggle is an amazing source of practical knowledge for data science skills. You can really practice a lot there and learn about how to actually model data and the different approaches and algorithms. But there's many things that you need to remember. Also, to hold the mic is also something that you need to remember. There's many things that you need to remember. After all, that what you see in Kaggle is not exactly the real world when you need to acquire data science skills. There's still a lot of things missing from projects that you see in Kaggle, and when I say Kaggle, I also mean data hack in general. The challenges that you see here. You already get data sets that were prepared. You already know what metrics you're optimizing for. You already have some task defined. And yeah, so there's a lot that in real world challenges you find yourself having to tackle. Whether it's defining the unique tasks that are not always well defined, whether it's preparing data sets for what you need to do or defining the right metrics to solve your problem, and et cetera, et cetera. Many times you find yourself having to find your own data and scrape data from many sources and prototype solutions, and then you make some experiments and you also need to manage them, and at some point you need to deploy this in production, and you also need to build something that would be robust to unseen cases. And then debug all those data-related mistakes. And so in this session, I'm going to talk a little bit just exactly about those use cases. Great, so all the use cases you'll see here come from the work at NetApp. I'll tell you a little bit about myself. I'm Adam. Yay, I love machine learning and deep learning and natural language processing more than everything. I lead the data science at NetApp compliance team, which was formerly Cognigo. And my background is in mathematics from Bali University. Now, I'll tell you a little bit about Cognigo. In our team, we began as a startup to develop a product that enables organization to make sense of and protect their sensitive data. We recently joined NetApp Innovation Center in Tel Aviv to bring the AI-driven data compliance product to even more customers and protect personal data of billions of people. So let's first introduce some key concepts of this talk. So you're probably familiar or not with the field of natural language processing. It's basically trying to make sense of natural language in a way that would enable machines to interpret them and process them. Now, a few words about the tools that we can use to model natural language. More or less, it's through time travel. So first, there are rule-based methods with lots of linguist experts trying to tailor lots of parts of speech and dependency parsing and thousands of rules and trying to keep up with incremental changes that are natural to language development. Then in the late 90s, machine learning models offered a more efficient way to model language, at least in documents, using bag of words and similar methods to count the frequency of terms. And in the past decade or so, recent development in computation power enabled the rise of deep learning and more ways to encode free text into vectors, more dense vectors. And I gotta say a few words about transformers. In the past year or so, there's all these guys. If you remember the guy at university who could memorize hundreds of digits of pi. And so think of this guy, but for corpuses of text, for the entire internet. And so basically they use multi-headed attention blocks on the task of predicting the next word given a previous sequence of words, more or less. Sometimes it's words, sometimes documents. So then and memorize enormous corpuses, and then completely by chance they happen to score highly on most natural language tasks. But when we're saying tasks, so we need to list just some of them, just so you get a sense, high-level pictures of what you can do with natural language. So more or less, you're probably familiar with some of them. The tasks on the right are considered more challenging. Yeah, so information extraction is basically the case of trying to extract only relevant information, structured information out of unstructured text. In information retrieval, you have another pile of unstructured text, and you need to retrieve, given some query, to retrieve the most relevant information within a large corpus of text. Now, we also must note that the idea of domains. Unstructured text come in many domains, and this will change. This will make sense in a few seconds. So you're probably familiar with many of those reviews data sets, for example, IMDb reviews. And so you can think of film reviews, right? So you can think of building a sentiment classifier for film reviews, and then to predict the sentiment of some given film review, and then trying to predict on a new sentence for another task, for example, hotel reviews, whether it's positive or negative. So take a sentence like, it was an incredibly scary experience, which can be okay for films, but not so great for hotels. Social networks. So it's very common to analyze large corpuses from social networks. By the way, have any of you heard of GPT-2 transformer? How many of you? Okay, GPT-2. Great. Okay, so GPT-2 is a transformer released this year by OpenAI, a team of brilliant researchers, with its lightest version of 300 million parameters. And this discussion you see here was made entirely by bots. Those bots were trained on massive corpuses and then fine-tuned on, oh, it's difficult to see here, but they were fine-tuned on different subreddits. And so you can see that each comment has some style that is definitive of the domain, the subreddit that it was fine-tuned on. This is just to get to make some sense out of the idea of the importance of domain. And finally, the domain we're dealing with is in our product is enterprise documents, and you have no idea how difficult it is for companies to organize the documents that they have. They have tons of unstructured information in doc and PDF and Excel, spreadsheets and images and code and whatnot. And they come in many forms. And up until a few years ago, they didn't really have such a great incentive to really try to protect their data, to really try to organize and manage their data. But in the past few years, something changed. And so the Cambridge Analytica scandal, which happened a few years ago, is a case where personal data of millions of people got into the wrong hands. And so it fell out of control, and following this case, which made lots of news, a strict series of data protection regulations came out and forced companies to manage their data more responsibly. Okay, great. So now that we understand the motivation for the solution, let's demonstrate some use cases I tackled during the research. So I'll cover briefly 3 of the main research projects I tackled, and I believe all of them demonstrate pretty well some of the real-world challenges. And also, keep in mind that they all are part of a system that should be deployed in a customer environment. So that's another thing, in a scale of billions of documents. So this is another thing that you should take into account. Okay. So beginning with the first one, which is personal data detection. Great. So the first use case is a pretty straightforward example of how deep learning can empower companies to comply with data protection regulations. And our goal here is to build some scalable pipeline that can map and detect such occurrences. And when you ask how to exactly specify what kind of information we're looking for, so thanks to the GDPR, half of the job is done because GDPR already has it specified for us, at least in some vague manner. And so it specifies the processing of personal data, specific categories of information that no company is allowed to process on European data subjects. And this means a lot for companies these days that have a lot of information and could be fined for hundreds of millions of dollars, and that hurts. So when you're trying to solve something like this, it's not trivial to solve this with deep learning, but you can think how difficult it can be for companies to actually find such occurrences in information. Now, when you look at something like this, what is the first method that comes into your mind when you attempt something like this? What do you think can work here? Anybody, any idea? What's that? Named entity recognition. Okay, named entity recognition can really help you with mapping the names, but it's not just the names, remember? You also need to specify one of those specific categories. Okay, so I'll give you a hint. This is about, you could match terms, right? You could say, okay, let's make a huge list of all potential terms. For example, terms representing religious views or ethnicity or things like that. And then just go ahead and problem solved, right? And that would be amazing. That would be very easy. But the thing is, and this in fact was the first draft of my work, but it didn't really solve the problem, because what you didn't take into account is the context of every sentence. And I figured it was time to break down this unique task into something a bit more solvable. Okay, so overall, when you examine different sentences, when you look at sentences that contain all such information, you can see that they all have some name or pronoun. Pronoun could be he or she, and they have the term that makes the sentence a potential for such information. And there's the rest of the sentence, which could make the entire sentence relevant or not relevant, right? But this also forces you to, once you do this, it also makes you think a little bit about what sentences you want to find and which sentences are less interesting and relevant. This is just the first step. The next thing is you can examine linguistic features like parts of speech or dependency parsing, and then come up with some rules, hopefully. But it didn't work in practice. It was useful to understand the problem better, I must say, but it wasn't enough. And so finally, I turned to the last result. deep learning. I'm just kidding. Solving this with data. And in previous step, I learned that false positive and specific domains are very common. So I made sure to include food reviews among the new data sets. And once you have massive corpuses, you can extract sentences just like that could be potential. And the next step is to label whether each sentence is relevant or not. This is just one method of labeling them. And that's the first part of it, of creating some data set. Now we can analyze and check the frequencies of those terms and repeat and add more sentences where needed. And this now where we go to the part of actually modeling this. And this is where I got to after several cycles of research. And so you can see this is a token level classifier of this task. Sequence labeling that can actually predict for each token, for each word, whether it could contain such information. And this is also a closed set of, by definition, a closed set of softmax outputs. And eventually, this is how it looks at the moment in production. Moving on to the next use case, which is document classification. So the motivation to this use case is what we mentioned before, to enable large organizations to map and categorize their entire storage devices on-premise and in the cloud. And so basically, it's text classification. And at first, this task may seem easy. And some of you are familiar with 20 newsgroups dataset and text classification. By the way, how many of you are familiar with this dataset and text classification task? OK. Great. So what you learn once you actually deploy something like that in production on customers' data, you figure out that there's a lot of data that is miscategorized and should have its own class. And reality hits you when you realize there's unknown unknowns that the model didn't encounter, and classes the model didn't encounter during training. So again, real-world data is very messy. And so it's necessary to remember this. Even if your problem seems trivial, and the pipeline you're experimenting with seems to work great on your training data, it's important that you also handle unseen cases somehow in your pipeline, and I'll explain this in the next slide. OK, great. So I have time. OK, so I found them useful to evaluate and also reduce the model's uncertainty. So for pipeline running in production, some of them are more suitable than others. So the first is probably the initial attempt when you just check the output vector of some classifier of your pipeline. And also, depending on how you're on the domain of your data and how it distributes, you could sometimes extract and model statistically different features. This is, for example, specific. When I had less data, I attempted to use some statistics to generate scores for each known category, depending on the number of words unseen during training, and to obtain some novelty score, how likely something is to actually belong to this category. Yeah, and there's also, you could ensemble multiple models. It works best when you have different features and different architectures inside the ensemble. And you could also add exactly the foreign classes, some of them, to your training data, and hope that this noise would help. And finally, if you really want to invest into the domain of uncertainty, you could also use Bayesian approximation. Perhaps you're familiar with Monte Carlo dropout by Eringal. So now we have a classification pipeline in production that can also know when some document should belong to others. But the next thing is we notice that in our product, once we deploy it, most of the documents actually go there. And so it's not too helpful. So I thought, is there anything we can still do about them to make sense of those documents? And this leads us to our final use case, which actually I broke it down into 2 tasks that had some common research of unsupervised learning. One is clustering similar documents, and the other is obtaining the most similar document given some query of a document. Okay, so remember it's real world, and you can't make any assumption on the data, right? Once you deploy the system in a customer environment on some storage, you don't really know what files are going to encounter them. And so classic methods for, for example, topic modeling did not work so well here. Didn't make much sense. So as a mathematician who likes to approach problems abstractly, I went into this with some strong assumption on how documents can distribute. And so I hoped for the best, and I assumed that there's a way to project raw documents neatly into some dense metric space in a way that would somehow maintain their contextual meaning and incorporate the domain knowledge as much as we can. And so you can understand that when you perform clustering on some data, what you need most to focus on is how you obtain this representation and how to obtain a really good representation. But for most types of the documents, you need to remember that you don't have labels at all. And also, once you come up with multiple ways to obtain representation, you need to ask yourself how to choose one representation over the other. What will make one better? How to evaluate. Okay, so just to visualize what I'm attempting to do here with relevant data so you can get a sense of it. This is a 3D projection of some label data from different data sets and from different categories within those data sets. And I'm looking for a way to represent new unseen data to encode such documents in a way that would maintain similar documents close to each other. And the idea of similarity is exactly what is difficult to encode. Great, so if you followed me by now, you probably realize that the qualitative notion of similar is highly subjective, and also that the geometric embedding of such space is difficult to tame without labeled data. But let me show you what you can still do. So you begin with some ground truth labels. These are not labels that we're trying to actually categorize by. We're not using those labels. We only use them as proxies for later evaluation. Then I picked some classic methods to encode documents. Some are sparse, like bag of words or TF-IDF, just to examine them, and some are more dense, like averaging the word embeddings of the entire document and things like that. In some of them I fine-tuned, in some of them I actually fine-tuned a language model over a small, relatively small corpus to incorporate some domain knowledge that is only relevant for this corpus. And once I had some encoding, I reduced the dimension of the vector so that it won't become too computationally expensive. Remember that clustering algorithms rely on metric distances, and in high dimension, that's super computationally expensive. And so finally, you can evaluate the resulting clustering using metrics I will explain next. Okay, so eventually, your goal is to get something like this. And those are clusters of documents that share some common ground. As you see, the clustering result here, the documents don't always, that cluster together don't always come from the same categories, but they usually come from the same data set, like in cluster number 6, the first one. And in this case, I chose to evaluate each and every cluster with some metrics that describe how homogeneous each cluster is, and how close it is to other clusters, to the closest clusters. Do you have time? Okay, so silhouette score is one metric to that you can point for first for each point in the cluster. This is just an example that I recommend if you want to get into the idea that I mentioned before. And now the same research for document representation also enabled me to derive another use case. So think how useful it could be if there was a document that you'd like to find very similar documents, but not just duplicates or not even near duplicates. So where you start from, just by their content. So you could build some engine where you first encode each and every document in some corpus to vectors, and then index those vectors in some k-nearest neighbors or approximate nearest neighbors engine that would be able to do those queries. So I'll focus on the first part, which is how to encode. So far, our available datasets and representation remain the same, but this time I'm using k-nearest neighbors engine instead, and some other evaluation metrics on retrieved documents. Okay, so let's see an example for what I'm expecting to get here. So do you see the text? Is it clear? Okay, so you have some document and you need to obtain its documents most close to it by content. And this is what it looks like. Okay, and this is a method to evaluate this. You could pick in random some documents, and then for each one, measure the average precision at k, which is very common in ranking systems. And you could also use Levenshtein similarity, which I found useful to actually, it comes from comparing two text strings to see how much you need to change one text so that it would become the other text. And it was very useful instead of actually reading lots of text to get a sense and to use something that doesn't rely on just the representation and encoding, but also on the actual content of the text. And yeah, okay, so the next thing, if you ask yourself how many documents you can obtain given some method, how many documents you'll get when you query a document, how many documents are within some radius distance apart, how many documents are within radius 0.5, how many documents are within radius 0.6, etc. And so on some data set, it looked like this, about 70,000 documents. It's a bit difficult to read for you the numbers, but the range here is between 0.6 and almost 2. And you could see that it pretty much makes sense if I use the normalized square Euclidean distance to obtain the distances, because for most documents, if you pick a large enough radius, you get many other documents. And at some point, you just get the entire data set, the entire corpus. Okay, so transfer learning in natural language processing. So what we did here basically, the notion of having one task and from some domain. And instead of just training for each task and domain, instead of training its own model and then having to reproduce everything over and over again, the idea of transfer learning, which can be used in many different forms, basically changes it to using a large enough or something that would solve a specific task in a way that the information could be maintained, the knowledge would be incorporated in a way that would be able to help to solve other problems. And so, as you can imagine, what I did before was some form of transfer learning to obtain the best representation I found here was actually the one that used latent layers of the classifier you've seen before, and which was trained on data from the domain on large enough data set. And this, in fact, was the most useful representation to actually solve the problem of clustering as well as similarity. Great, so Sebastian Ruder also wrote an amazing thesis that I was very inspired by about transfer learning in natural language processing, and I encourage you to go over it if it interests you. And so in summary, we went over context-based approaches and how you maintain reliability across domains. I also demonstrated what you do when you have some uncertainty in the data, in the model, sorry. And also how to use distance-based metrics, distance-based approaches in metric spaces in a way that would preserve knowledge for your task and domain. Okay. Thank you guys so much. Thanks for your attention.